I'm a strange guy.
Really?
Yeah, I worry. I mean, little things bother me. I'm a worrier. I mean, little insignificant details. I lose my appetite. I can't eat.
One of my idiosyncrasies is that I find it difficult to hold ideas in my head which are supposed to cohere, but for which I cannot observe the coherence. Now, for the most part, when you're studying mathematics, one of the whole points of mathematics is to present this very coherent view of number and then apply it in different situations. But there were a few situations during my more elementary education where I never saw what the coherence was. And the point of this talk is to attend to that. So, for instance, you might say something like, what is 2 to the pi? Well, you'll recall from grade school that 2 to the third is simply 8. Why? Because 2 times 2 times 2 is equal to 8. And similarly, you could define things like, well, what's 2 to the 0? And really the only reasonable way is to define that to be 1. Well, what's 2 to the negative 1? Well, really the only reasonable way to define that would be 1 over 2 to the 1. And similarly, 2 to the negative n is going to be 1 over 2 to the n for positive n, positive integer n. And then as you go along, it would only make sense to define fractional powers, rational powers of 2, as being involving roots. So you would find out that 2 to the 1/3, the only reasonable way to define that so that everything worked out in a coherent sense would be 2 to the, would be the cubed root of 2. Something like that. So all well and good, but now what happens if when you take 2 and you raise it to an irrational power, something like pi? What would occur then? Well, it's not obvious. Now you might say something like, well, look, you can approximate pi by saying, well, you know, at 0 decimals it's 3, at 1 decimal it's 3.1. 3.1 is, 31 over 10, and that's well defined, and so you can use this. And then 3.14 is 314 over 100, so you can take 2 to the 314th over 100. Now, admittedly, the arithmetic's getting pretty terrible here, but at least it can be done, right? And so then you might say, okay, well, if we want to include irrational powers for 2, taking 2 to irrational powers, we're going to take the 2 to the x function and extend it continuously, or some magical phrase like that. And, that's good enough, say, for when you're in pre-calc. But if you're going to be a professional mathematician, you should really have a much more precise understanding of what that is. And speaking of pre-calc, pre-calc is often when you first encounter this other letter number thing, although in this case it's not a Greek letter, called e. And you pretty soon learn that these two expressions here apparently are equal and apparently equal e. But it's not immediately clear what e is, how it is actually defined, say, in pre-calc. You just learn it's something like 2.71 and some other stuff, and mathematicians like it for reasons, and you're like, yeah, okay, I want to pass the course, so I just go along with it. But it's not immediately obvious why you care that these two expressions are equal to each other, and if they are, that this value here has this fun little property that when you integrate 1 over x from 1 up to it, it equals 1. It's like, what exactly is going on here? And so that's with exponentials and logarithms. Now, it gets even worse with trig functions. So you might say something like, well, what is sine of 2? And you don't know, because you only learn what the sine of 5 different things is. You'll learn what the sine of 0 is, pi over 6, pi over 4, pi over 3, and pi over 2, and then you just kind of make that go around the unit circle. And let's talk about the unit circle for just a moment. So, all your life, up until you take pre-calc, you learn that there's 360 degrees in a circle, and that's basically how people parameterize turning around. And then you get to pre-calc, and they're like, no. We're not doing degrees anymore. We're going to do arc length. And you go, arc length? What's that? Well, we know that the circle has circumference 2 pi, and you go, well, yeah, if you say so. I'm still not really sure what pi is and how it's defined, but sure, why not? Well, what we're going to do is, instead of measuring 360 degrees around, because the length of the circumference here is 2 pi, we're going to measure in terms of 2 pi around, and that's going to take you once around the circle. And you go, okay, it's a little odd, but I guess I can do that. And they go, wait, we're going to do more. We're going to keep going around the circle to 4 pi and to 6 pi and to 8 pi. And you go, well, isn't that just going to give you the same values? They're like, yeah. And that's how you get periodicity here when you map that function onto the real line. And if you go backwards, we're going to call it negative 2 pi and negative 4 pi. And you say, okay. So that gets me my periodicity. So apparently the sine function is defined for all these numbers, but I can't even say what sine of 2 is. Like, what's going on here? It seems like we're introducing a lot of mysterious stuff. So I thought that after getting an undergraduate degree in math, or certainly after getting a graduate degree in math, that these ideas would cohere, and eventually I would get a nice precise definition of all of these things, the transcendental functions, values like pi and e and stuff like that. And I didn't, and I realized I wasn't going to, because I was far enough into grad school where we didn't bother talking about pre-calc stuff anymore. So I had to figure it out for myself. And so that is the point of this talk, is to show you the path of how to start with precise definitions for the transcendental functions and then recover their intuitive properties. And so I'm going to be saying really basic stuff in this talk, like, oh, the area of the circle is pi, the unit circle is pi, and its circumference is 2 pi, and 2 to the 4th power is 16. I'm going to be saying it very triumphantly, even though they're very, in a certain sense, well-known facts. But the reason why is the point of this talk is not to show you the conclusions. The point of the talk is to show you the path from the precise definition to the conclusions with which you're already familiar. So, without further ado, let us begin. We'll start with exponentials and logs. And here we go. So, what we're going to do is we are going to make use of infinite series. Everything is going to be defined in terms of infinite series. And so the level of technicality for this talk is really just Calc 2. That's when you do infinite series. So we're going to define things in terms of infinite series and slowly bootstrap our way up to the conclusions with which you're already familiar by making clever definitions and using clever proofs. Now, it should be observed that the material for this did not come from a single text. I wasn't even able to find a single text that gave a real rigorous development of this. Rather, I will talk about the texts which I have used as I use them throughout the course of the talk. So what you do is you define e to the x, the exponential function. You simply define it, and you write it suggestively as e to the x, x being the superscript, as opposed to just e of x, which is typical functional notation. You define it to be an infinite series. And when you do this, you really only know one thing. You know the value of this function here at 0, because you plug in 0 for x and you get 1 out of it. And so from this, we have to argue our way forward. So the first thing to do is to say, well, we're going to define e to be e to the 1. And that's what e is going to be. And so the definition we're taking for e here is that infinite series definition. Or infinite sum, I should say, definition. Well, what else can you learn from this? Well, one thing you can learn is you can say, well, I know by the ratio test that this series works everywhere on the real line. So the function is defined everywhere on the real line. All well and good. And I can, because it has an infinite radius of convergence, I can do term-by-term differentiation. And so when you do term-by-term differentiation with this guy, one thing that you observe is that, oh, this function is its own derivative. And that's a very useful observation. And so using that observation, we're now going to start to derive some of the rules with which you're familiar for exponentiation. And so for the first one, to get that the exponent of a sum is the product of the exponentiations, we're going to define this cute little function here. And so the idea for this proof comes from John Conway's complex analysis. So he wants to prove that rule, and he says, okay, here's what we're going to do. We're going to define f equal to e to the x times e to the y minus x for some fixed y in R. So take your favorite number in R, that's going to be y, and then you're going to define this function here. And we're going to use this technique 3 times in the course of this talk, which is, again, because we have the goal in sight, we are going to define a clever function, and we're going to use the fact that if you differentiate something and you get a 0, then the original function is constant, which means that in particular, the original function is equal to whatever it's equal to at 0. So you define this function here and you differentiate it, and what happens is when you apply the product rule and the chain rule for the second term here, or the second factor here, as well as the fact that the derivative of e to the x is e to the x, what you find is that when you take the derivative of this function, you get that f prime is 0, which means that f prime is a constant, which means that when I evaluate f at 0, I should get whatever the function is equal to, which is apparently e to the y. So, if that's the case, well then what I can do, for instance, is I can reparameterize up here. So if I let x equal a and y equal a plus b, plugging those values in up here, and recalling that this whole thing here, this product here, is equal to e to the y, I recover this rule here. So, now we're making some progress. Well, what can you do with this rule? Well, among other things, you combine it with this observation. You say, well, look, e to the x is this infinite series. In particular, it's bigger than 1 plus x for positive x, which means we know that the limit of this thing is infinity at positive infinity. You take this idea, you combine it with this formula here, and this tells me that e to the negative x is apparently 1 over e to the x for all values of x. And so therefore, because at the positive infinity, it's going to infinity, at negative infinity, e to the x is going to 0. Okay, so now we're good, and moreover, we know that the range of this function contains positive numbers, and we know there are no negative numbers because we know that the function is 1 at 0, positive for positive x values, and for negative x values, this formula here tells us that it's still positive, just less than 1. So the range of the exponential function, as we've defined it, is all positive reals. And moreover, because it's all positive reals, and it's its own derivative, it is therefore 1 to 1, it's increasing in 1 to 1, which means that it has an inverse, which we define to be the natural logarithm. So, the natural logarithm is simply defined as natural log of x equals y when e to the y equals x. All well and good. And so we're going to use this explicitly here and implicitly later on in the talk. We're going to say, well, look, what's the derivative of natural log of x? And the answer is, well, we already have a general formula for the derivative of the composition of functions. And in particular, when you compose a function with its inverse and get x, you can calculate the derivative of the inverse function in terms of the derivative of the original function. And so what we see here is that the derivative of natural log of x is in fact 1 over x, using that property. And because of that, because the derivative of natural log of x is 1 over x, that is precisely what allows us to write this integral here, that 1 to the e of 1 over x is equal to 1. Why? Because when you evaluate natural log of x at 1, you get 0, and when you evaluate natural log of x at e, you get 1. With these definitions for the exponential logarithm now, what we can do is we can define general exponentials. So a to the x is now going to be equal to, it's going to be defined to be equal to e to the x times the natural log of a. And log base a of x is simply going to be natural log of x divided by natural log of a. And so, for instance, going back to the beginning, when I said 2 to the third power is equal to 8, that's no longer obvious here. Using the definition that we have here, 2 to the third is going to be e to the 3 times the natural log of 2. It's not immediately obvious that that's equal to 8, although we will show that it is. So with these definitions in mind, now we will recover the intuitive properties of these functions. So take your favorite positive integer, and now you can play this game, which is that a to the m, by definition, is now going to be e to the m times natural log of a. But this is just the natural log of a added up m times. But the exponential of a sum is the product of the exponentials. But e to the natural log of a is just by definition a. And so now we have recovered the idea that you take a number and you raise it to a positive integer power, you're going to get that number multiplied by itself that many times. And with this in mind, you can play similar games and show that similarly a to the 1 over m raised to the m just simply gives you back a, and a to the m times a to the negative m simply gives you 1. And finally, for the final, not definition of e, but representation of e.
You have the esteemed privilege of being the first to see my next form.
For the final representation of e, simply use the fact that the derivative of natural log of x plus 1 at 0 is 1. And so that's what you have on the left-hand side here. And then on the right-hand side, you simply write out the definition of derivative. You use your rules of logarithms, proven in the exact same way that you prove your rules of exponentials right here, to derive this formula here. Because the function is continuous, that allows you to exponentiate both sides. When you exponentiate 1, you get e. And when you exponentiate this side, you get this representation for e. And that is how you recover your intuitive properties of exponentials and logs from the original definition of a series, using a series for e to the x. So now we move on to trigonometric functions. And we will take the exact same approach here. We're going to define sine of x to be equal to this infinite sum, and we're going to define cosine of x to be equal to this infinite sum. So, what can we conclude? Well, again, at the beginning, all you really know is that, well, I can put in 0 for x, I get 0 for sine, and I can put in 0 for x and cosine, and I get 1. So that's about it. But now we'll make the exact same observation we made previously, which is that the radius of convergence for each of these functions is, in fact, infinite, and that allows us to do term-by-term differentiation. And because we can do term-by-term differentiation, we're going to realize that the derivative of sine is cosine. So when we do term-by-term differentiation on this, we get that, and when we do it here, we get that. And that's going to allow us to get back, to recover the classic identity that sine squared plus cosine squared is in fact equal to 1. And now we use this technique the second time. We define f of x equal to this. We take the derivative. We find out that because the derivative of sine is cosine and the derivative of cosine is negative sine, what we get is that this derivative is equal to 0, which means that this function here is equal to whatever it's equal to at 0. But when you plug in 0, you get 0 here and 1 there. And therefore, this function is identically equal to 1. And now this will be the third time we use that technique. What we're going to do is we're going to prove a lemma, and we're going to say, look, suppose that you have a function such that the function plus its second derivative is equal to 0, which does hold true in the case of sine and the case of cosine. But it's also true that the function and its first derivative at 0 are also equal to 0, which does not hold for the sine and the cosine. So obviously sine of 0 is 0, but its derivative at 0 is 1, and then the cosine at 0 is also 1. But suppose you had a function where all of these things held. Well, then it turns out that that function is just identically 0. So how do you show that? Well, again, you define this nice cute function here, g, to be equal to f squared plus f prime squared. Then, when you take its derivative, what you get is this term of, or this factor of f plus f prime, f double prime, which is equal to 0, which means then that g itself is a constant function. Well, what's it equal to at 0? And the answer is, well, by definition, it's equal to 0. However, because g is bigger than f squared must be 0, which means that f is 0. Now you might say to yourself, well, that's a really odd lemma. How are you going to use that? And the answer is, we are going to use it to prove our sum and difference formulae for the sine and cosine. So this is the formula for the sum of the sine of two numbers. And so what you do is you simply take the formula for the sine of two numbers, you move everything to one side, and you simply call that g of x for your favorite y. And when you define g of x that way, you find that g of x has exactly the requirements of the lemma, that g plus g double prime is equal to 0, which is equal to g of 0, which is equal to g prime of 0. And similarly, you can do that for the cosine to get the cosine of the sum of two numbers. And so once you have these formulae here, you can recover things like the fact that the cosine is symmetric about 0, and you can recover the fact that the sine is anti-symmetric about 0. So, it should be observed as well that this treatment here kind of comes from both Fitzpatrick's Advanced Calculus book and Georgy Shilov's Real and Complex Analysis. In the case of Fitzpatrick, what he does is he says, let's suppose that these two differential equations, and he writes them down on the page, let's suppose that these two differential equations have solutions. What can we say about them? And then derives these ideas. Shilov, on the other hand, just takes some functional equations and says, let's pretend that there are some functions such that these equations hold. What can we deduce? And so what you're seeing here is sort of the amalgamation of what they have done. So now with this, we can proceed, and we're going to make a few observations here. One is that sine squared, of course, is bounded below by 0 and bounded above by itself plus cosine squared, which means that both the sine and the cosine, because you can make the argument for cosine, are bounded between -1 and 1. Okay, so now we come to the difficulty of what to do with pi. So pi in this case we have yet to define, but now we're going to move on the path to doing so. And to do that, what we're going to do is we're going to say, well, look, we recall the mean value theorem. So the mean value theorem says that if you present me with an interval, say 0 to 2, if I evaluate a function at the end of the interval and subtract it from the value at the beginning, divided by the change in x, change in y over change in x, that there's some point in between those two values, some point in between 0 and 2, such that the derivative of the function evaluated at that point equals that ratio. All right. So sine of 0 is 0, and 0, of course, is 0. So really what this is saying is somewhere, I'm not saying where, somewhere between 0 and 2, there is some number z such that twice z is equal to sine of 2. All right. Well, what can you do with this information? Well, because we previously proved the sum formula, we know what the cosine of a sum is equal to, and we know the fundamental identity that sine squared plus cosine squared equals 1, we can deduce that cosine of 2z, whatever it is equal to twice cosine z squared minus 1. Well, but we know that 2 times cosine of z is apparently equal to sine of 2. And so then we get sine of 2 times cosine z. And we know that both the sine and cosine are bounded between -1 and 1, which means the The largest that this product can be here is simply 1, because each of the factors in the product is at most 1, which means that this whole thing is bounded above by 0. So either cosine of 2z is 0, in which case we found a 0 of cosine, because up until this point, we really don't even know that cosine takes the value 0. Because all we know at this point is that cosine of 0 is 1. Maybe it never takes the value of 0. But now we know that it must take the value of 0 somewhere, because either cosine of 2z is 0, or cosine of 2z is less than 0, which means that somewhere between 0 and 2z, cosine takes a 0 value by the intermediate value theorem. And so what we're going to do is we're going to say, look, we're going to define pi, so this is where pi comes into being, but we're going to define it analytically instead of geometrically. We're going to say, look, pi is going to be the number such that half of that is the smallest positive number such that cosine of pi over 2 equals 0. So again, we know that cosine of 0 is 1, and we know that the function is continuous because it's differentiable. We know it's continuous, which means you don't have a bunch of zeros accumulating near x equals 0, zeros of cosine accumulating near x equals 0. So there has to be a first time that the cosine function is 0 on the positive reals, and we're just saying, look, we don't know what that is, but whatever it is, we're going to define pi to be twice that first time. And so pi is defined such that pi over 2 is the smallest number such that cosine of pi over 2 is equal to 0. Now, we know that sine squared plus cosine squared is equal to 1. If cosine of pi over 2 is equal to 0, then sine of pi over 2 has to be either 1 or negative 1. So which is it? Well, we're going to play the same game invoking the mean value theorem and say, okay, instead of going between 0 and 2, as we did previously, we're going to go between 0 and pi over 2. And there's some c in there such that the derivative of sine, which is cosine, evaluated at c, is equal to sine of pi over 2 divided by pi over 2. So now we're in good shape because we've got our sine of pi over 2 here. And that's apparently equal to cosine c times pi over 2. Now, what can we conclude? What was the point of this? Well, remember, pi is defined to be positive, so pi over 2 is positive. And c is between 0 and pi over 2. Well, since pi over 2 is the first time that the cosine is 0, between 0 and pi over 2, the cosine is positive, which means that in particular, the cosine is positive at c, which means that sine of pi over 2 is something positive times something positive, which means it's positive, which means that sine of pi over 2 is equal to 1. Okay, with this in mind now, what we're going to do is we are going to now recover the geometric significance of pi and the trigonometric functions. And so we're going to play some games. So here's one. We're going to take pi over 2. We're going to represent it as pi over 3 plus pi over 6. And then we're going to use the sum formula. So the cosine of pi over 3 plus pi over 6, we already have our sum formula. And so we know that cosine of pi over 2 is apparently equal to this right here. But by definition, cosine of pi over 2 is equal to 0. So this equation here holds. And then we're going to play a similar game. We're going to say, look, pi over 6 is equal to pi over 3 minus pi over 6. So using the difference formula for the cosine, we are going to get this expression here. Now, why is this useful? Well, because look, both of these terms here match up with each other, all we've done is change the sign. SIGN. So what this means then is that we can add these two equations together here, and the parts with the signs are going to cancel each other out, and you're going to be left with twice cosine pi over 3 times cosine of pi over 6, and that's going to be equal to cosine pi over 6. Now, we would like to simply divide both sides by cosine of pi over 6, but we're kind of nervous that, well, what if cosine of pi over 6 is 0? Then we can't do that. But then we remember that cosine of pi over 6, well, pi over 6 is less than pi over 2, which means that because it comes before the first 0 on the positive reals, whatever cosine of pi over 6 is, it's not 0. And so we can divide both sides by that, and we can divide both sides by this 2 here, and that's how we get that cosine of pi over 3 is in fact equal to 1/2, which means that the sine of pi over 3 has to be equal to plus or minus square root of 3 over 2. And using the sum and difference formulas, as well as the asymmetry of the sine and the symmetry of the cosine, you can figure out where the intervals of positive and negative values are for cosine and sine. The exercise is left to the viewer, and you'll find out that sine of pi over 3 is equal to square root of 3 over 2. And you can do similar trickery for all of the other standard values, pi over 4, pi over 6, and so on. And so again, it should be observed that this kind of reasoning here came from Shilov. Okay, so we're in good shape because now we have recovered all of the values of the sine and cosine at their sort of canonical values that we learned in pre-calc. So how are we going to get the rest of it? How are we going to get the geometric significance of pi? How are we going to get the trigonometric significance of these functions since they've been defined in terms of power series? And the answer is it's all going to come from just this fun little function here. We recall that if you want the equation of the unit circle, at least the top half of that is given by y equals the square root, the positive square root of 1 minus x squared. And you say, well, if pi is to have the geometric significance it has, then the area under this curve here should be equal to pi over 2, or the area of the whole circle, if you can imagine the second half of it down here, should be equal to pi, and the circumference here should be equal to pi, or the circumference of the whole circle should be equal to 2 pi. So how do we see that? Well, we just go about our work, and we recall all of our tricks from Calc 2 to do our integrals. And so we're going to integrate this function here. We're going to integrate the top half of the unit circle from -1 to 1. We're going to multiply that by 2 to get in the bottom part of the area. We're going to do some trigonometric substitutions here. We're going to let x equal sine of u. And then we're going to go, well, wait a minute, 1 minus sine squared, well, that's just cosine squared. And so this gives us cosine squared here. We use the half angle formula here, and lo and behold, we get pi there. So you just use your standard tricks to do integrals from Calc 2 to get that the circumference is going to be 2 pi. What you're going to do is you go, well, what is circumference? And you remember, yes, that comes from the arc length formula. So if we want the arc length of this guy here, the arc length formula says, well, integrate that guy between -1 and 1. And I've represented this as a limit for technical reasons. But basically, integrate between -1 and 1 the square root of 1 plus the derivative squared. That's the arc length formula. Okay, so you do that. And when you take the derivative of this guy and you square it, and you add 1 to it, and you take the square root of that, so a bit of arithmetic, but mere algebra, between here and here, what you get is this expression here, and you say, well, what can I differentiate in order to get 1 over the square root of 1 minus x squared? And then you remember what we did earlier to calculate the derivative of the logarithm is that what you can show, in fact, is that while the sine function is, in fact, periodic, between negative pi over 2, where it's equal to negative 1, and pi, where it's equal to 1, in that interval, the sine function is, in fact, invertible. And its inverse is simply called the arcsine, or the inverse sine function. And when you play the game that we played earlier, what you find is that the derivative of the arcsine is precisely 1 over the square root of 1 minus x squared. Which means that this integral here is simply this difference here. And as we just said, arcsine of 1 is going to give you pi over 2, because sine of pi over 2 equals 1. And arcsine of negative 1 is going to give you negative pi over 2, because sine of negative pi over 2 is negative 1. And so here you get pi over 2, and here you get negative pi over 2. You add them together, and you get pi, which is precisely what we want. And so this is the arc length from positive 1 to negative 1. And so that's going to give you the arc length of the top half of the unit circle, which is exactly pi, which is what we wanted. So pi indeed does have the geometric significance that it had previously. Okay, so going back to the picture here, now let's talk about the trigonometric significance of the sine and cosine. And so if you look here at the graph, well, again, they're called trigonometric functions. Why? Because they're originally thought of in terms of the triangle. And so here's a triangle. It's just at some point here on the unit circle. And so this length here is going to be L, and this height here is going to be H. And recall, at the beginning, what we said was the sine and cosine, the inputs were thought of as arc lengths, right? Some amount of traversing of the perimeter of the unit circle. And so that is how we will recover the intuition, the meaning of the trigonometric functions as coming from a triangle, is we are going to, if you will, plug A, so A is the arc length of this piece here, into the sine function and into the cosine function. And when we do that, we should get out L for the cosine and H for the sine. So, because we're thinking about arc length, we are once again going to use the arc length formula. So again, we take the square root of 1 plus the derivative squared of this function here. We do the usual stuff. So we're integrating now 1 over square root of 1 minus x squared between L and 1 minus h. And we get this expression here. And so, once again, the arc sine of 1 is going to give you your pi over 2. And so what have we deduced here? We've deduced that the arc length, that value A that we saw earlier, A is equal to pi over 2 minus the arc sine of L. But what that means then is that, arranging your terms, L is apparently equal to the sine of pi over 2 minus A. But we have a formula for the sine of a difference, and when we apply it and we remember that pi is defined such that cosine of pi over 2 is 0, and that sine of pi over 2 is 1, that gets us precisely that cosine of A is equal to L. And similarly, the sine of A is going to be equal to H. And so therefore, using integration and its interpretation as area, you recover the geometric significance of pi, and using the arc length formula, you can recover the trigonometric meaning of the functions, even though they were defined in terms of the power series. So again, for the viewer, the references for this are as follows. Conway gave us that clever little function to show the rule that the exponent of a sum is the product of the exponents. Fitzpatrick and Shilov both give a nice exposition about the definitions of the trigonometric functions. Fitzpatrick in terms of solutions of differential equations. Shilov in terms of assume that some functions satisfy certain functional equations. So following their development, we were able to create the path from precise definitions of the transcendental functions and then recover their intuitive properties. And so now everything coheres. I am Mean Metal X, and I thank you for watching Full Metal Analysis.
Don't break the sucker!